started talking about discriminant functions last time, and we talked about some simple distance-based metrics that we could base those discriminant functions on. So what I want to do now is I'd like to go through the development of the Gaussian maximum likelihood classifier. Right? It's going to use the same set of decision rules that we used last time, where we were comparing that G function for each of the land cover types that we were looking at. But now the value that we're going to have represent that discriminant function is going to be probability based rather than just strictly distance based. There's a distance component to this. That's part of the probability, but the final discriminant function itself will be probability based. All right, so everything that we went over last time, clear? Make sense? All right. So I know you probably have all seen this before, but I just want to go through a little bit of basic probability theory leading up to the Bayesian theorem. And I just want to make sure we're on the same page as far as terminology goes. Now, just to point out where I follow, what textbook I'm actually following. It's not the textbook that you have for the class, and it's not on the reading list. Rats. Okay. Let me point you to a really good book. It's this book right here. It's called Remote Sensing Digital Image Analysis. It's by John Richards and Ethan G. They're both over at the Defense University in Australia. Juping actually visited here a couple years ago to give some lectures. But this book is it's terrific. It's only about this thick, it's only a couple hundred pages. So I mean, there's not a lot of material in there, but what's in there is covered really well. And what they have a all right, so they cover a little bit about sensors and sources, and then a little bit about registration, right? And then they start to talk about multispectral and how to look at those things, unsupervised classification, supervised classification, a little bit of standard image processing that you're probably doing right now in DIM with histogram matching, histogram equalization, that sort of stuff. And then they go through some frequency domain material in here. But it's all very applied to the remote sensing problem. And this chapter right here on supervised classification is actually the terminology I'm following in the notes that I'm using from the image processing class. So if you have a chance, and if you have a chance, you have $92 extra that you don't know what to do with. This is an awesome book. It's my go-to book. This is the one I use more than anything else that's on my shelf. So I don't get any kickbacks from this, but it's a really good textbook. And the appendices in here are really the best resource I found that explain principal complex analysis. And that's one of my favorite things. Is Appendix A goes through the basics of PCA, and you do it in a very, very straightforward sort of way. It just makes it clear. Everybody that I know that reads through it, they're like, oh, okay, I'll get it. So, like I said, you have 92 extra bucks. That's pretty good. All right, so probability theory. If you go back and think the first time you took a class in statistics or probability, you started talking about different probability density functions. And you looked at uniform functions, Gaussian functions, Erlang functions, and all kind of different functions for predicting probability of certain kind of events. And probably any time after that class, the only distribution you ever used again was Gaussian distribution, right? And there's many good reasons why folks always roll back to that. It's very well understood. It's easy to represent. If you have enough data, most data starts to represent, Gaussian distributions. Remote sensing data isn't one of those data sets. I mean, making Gaussian assumptions about remote sensing data, if you ever look at histograms of any of the bands that you get from a multispectral or hyperspectral sensor, if you ever plot the digital counts from those in an ensemble fashion, you'll surely see multiple modes all over that histogram. All right, well, that's a whole bunch of different populations of observations that you're making. You're looking at all kind of different land cover classes when you do just a single band histogram from an image. But if you start to break it up and you start to segment that scene into pixels that represent different sorts of land cover types, then plot those histograms. They tend not to be multimodal, right? They tend to have a single mode, right? As long as you pick them wisely. If you pick grass in the sun and in the shade, well, now you'll have a multimodal histogram, right? But if you're smart about picking your samples and saying statistically, even though culturally that's grass, statistically I know that's not the same class, right? Because its brightness is very different, right? So if you pick things like that wisely and you start to look at the histograms, you might start to convince yourself that they're Gaussian in nature, right? I had a master's student a long time ago. Let's see if her thesis is down here. See an Elizabeth Fry.
17.
17? Sweet. There it is. An examination of distributional assumptions for Landsat TN imagery. There's no, unfortunately, I don't have, that's right before, his PDF started right after. It was hard to get a PDF in 1995. So it is on the bookshelf in the reading room, and we do have, John, I think John Schott and myself probably still have a hard copy of that if anybody wants to read it. But what she did was she looked at how critical is it that you have Gaussian distributions. Right? If you assume that data is Gaussianly distributed and you use it to do classification, and it's not truly Gaussian distributed, how much of a penalty do you pay because of that? Right? And there was definitely changes. I mean, she did a lot of this synthetically, so she modified a distribution of let's say, class 1, class 2, class 3 pixels, started off with them all Gaussian, slowly modified the distribution so it became non-Gaussian. You saw definite degradation to the classification accuracy. But when it comes down to it, it performs okay, right? So you'll get 90%, 85% classification accuracies when you do independent tests and look at your actual pixels and say, I know this pixel was grass and it classified as grass. I know this pixel was asphalt and classified as asphalt. You'll get very high classification accuracies even though the data is not Gaussianly distributed. All right? So it's one of those things that I want you to always be cognizant of, that you are making this big assumption when we're going to use Gaussian maximum likelihood to do classification. And I also want you to be as critical of it as you can. Right? It works okay for remote sensing data, but if you go off and you want to use this on texture data, you want to use it on SAR returns, you want to use it on infrared data, data sources that might be different than something from 0.4 to 2.5 microns in that wavelength band. Then you really got to start to take a look at these distributions again and see if they are even remotely true. Right? So I always want you to look at the data and make sure that you're making some reasonable assumption by assuming the data is Gaussian. All right. So that being said, let's assume the data is all Gaussian, okay? And let's take a walk through this and see how it all comes together. All right. So if we just look at the simple term P of X, right? That's the probability that an event X occurs. And the way that the terminology is all written here, at least what I tried to do, I think I'm consistent throughout the slides here, is if it is a non-boldface term, that means it's a scalar quantity. And if it's a bold-faced term, it means it's a vector quantity. Right? So if x is our n-dimensional pixel vector, so our vector that's filled with all the band data for that particular pixel, then what does that represent? It's the probability that a pixel exists in n-dimensional space at a position designated by x. All right, so it says that with a digital count of 48, 72, 37 in a 3-band system, that's the probability that there is a pixel at that point in space. Right? These are very highly dimensional spaces, right? You've done stuff like this with single bands, right? You compute histograms all the time. And the histogram is the probability that a pixel has a digital count of 28. And you've done that in a one-dimensional case. So we're just going to make the extension now and do, what I just described there, that would be a 3-dimensional histogram. But you can imagine when we have hyperspectral data, you can have a 224 dimension histogram. Big difference is these histograms, as you go to higher and higher dimensions, start to become more sparsely populated. Right? I mean, consider an 8-bit system, 256 levels in each of red, green, and blue. Right? So that's 2 to the 24th possible positions in that histogram. That's a lot of positions, and the number of pixels is much, much smaller than that, even some of the biggest images. So you need to keep that in mind, that sometimes these distributions that we represent are just going to be very sparsely populated. All right, so we often want to know the probability of event occurring given some other event has already occurred. Right? And that's a concept that you've seen before called conditional probability. All right, normally you denote it like something like this, where you say the probability of X occurring given that Y has already occurred. In the multispectral case, or in the multivariate case, we could represent that. And specifically, for what we're trying to do right here, land cover classification, what I'd like to represent as a conditional probability is the following. It's the probability that X has occurred, right, given that I'm looking at class type I. Right? Remember that omega sub I is the class that we're looking at. All right, so this represents the probability that a pixel of type omega I exists at a position described by X in dimensional space. So now, what is the difference between this and this? This is a histogram of all the pixels in your scene. Right? This is an n-dimensional histogram of all the pixels that are in your scene. This is an n-dimensional histogram of just the grass pixels in the scene, or the water pixels in the scene, or the concrete pixels in the scene. Okay? So it's a histogram based on class type. Agree with that? All right. So if the complete set of those conditional probabilities are known, right, these are often called the class conditional probabilities. So the probability that X occurs given that we're looking at a particular class type. Then P of X can be found. Right? So let's go through and let's find P of X. P of X, remember, was that histogram of all the possible pixels in the scene. All right. So remember, this was the conditional probability we just spoke about. What is this? Probability of omega I. It's the probability of a pixel type omega I exists in the image. Right? So that's just a probability that a water pixel is in the image, a probability that a concrete pixel is in the image. Right? This is what we referred to the other day as an a priori probability, right? Without any distributional or data knowledge of the scene. This is just, I know I just took an image at this particular latitude, longitude. I know from USGS cartographic maps that that's right on the border of Lake Ontario and Irondequoit. So I know half the scene is water and I know half the scene is non-water. Right? So I know a prior probability of pixel being water, and I know a prior probability of the pixel being non-water. break it into those 3 classes. All right, so this product that we have right here between the class conditional probability and the a priori probability is the probability that a pixel at position x in n-dimensional space is an omega type pixel. All right. Now, let's go ahead and take that product, and if we take that product and we sum them up over all class types, right, what we'll wind up with is the probability of a pixel occurring at any particular point in space, because we've summed over all possible pixel points.
Will you repeat that?
Yeah. So this term right here is the probability of a pixel existing at point x, so at a position in n-dimensional space, right? Given that the only pixels that I'm looking at are of a particular class type.
So, could I rephrase that?
Yeah,
You're
absolutely.
saying what is the probability of that location being from class A, from class omega I?
Not quite. And that's why I want to go over the terminology. It's the probability that a pixel exists at that point in space, given that the only pixels I'm looking at are of class I. What you just said, the probability that that pixel is of class I, given it's that point in space, is actually where we want to get to. That's the classification answer,
Okay.
right? This isn't. This just says this is a histogram of pixels in type I, of class type I. That's all it is.
Okay.
So the very subtle difference is this is the probability that a pixel exists at point X, given I'm only looking at water pixels.
Okay.
But imagine, there could be a pixel there that's concrete, right? It could have exactly the same set of digital counts. Unlikely, but it could happen, right? So that's why I want to make the distinction. So you could have a pixel at X that's water. You could have a pixel at X that's concrete. This represents the probability that you'll find a pixel at that location, given you're looking at a particular class. Okay. Now it turns out that this is actually something you can derive, right? I can go in the scene. I could highlight concrete pixels. I can compute a histogram and hence a probability distribution, right? So I can derive this from data. And we'll get to the other one that you mentioned right on the next slide. All right, so if I add up all those probabilities, I weight them by this prior probability that it occurs, I wind up with the overall histogram of all the pixels in the scene. Now, if we take that product, another way of representing that product that we had on the previous page is in this terminology right here, which you've probably seen before, called joint probability. Okay? So the product of these two, the histogram of a particular cover type and the probability that that cover type exists, is written like this, terminology-wise, and it represents the probability that a pixel occurs at that position and that pixel is the type omega I. So this is the probability that there is a pixel at X and it's from class I. So we're still not quite to the definition you wanted to mention, but we're almost there. All right, so let's just go over these one more time. P of omega I is the probability that an omega type pixel occurs in the image at all. That's what's called the a priori probability. P of x given omega I is the probability of finding a pixel at position x, given that we're interested in pixels of that type. That's the histogram of pixels of a particular type that you can derive from training data. P of x and omega I is the probability that a pixel occurs at position x and that the pixel is of that type. So that both of those things occur at the same time. All right, so We take those three definitions, and let me just rewrite it up here. So we have that joint probability again, but now, you see anything different?
Yeah. Oh,
You switched the.
Yep. Switch the terms around. Okay. So here, what we have is the probability of omega I and x, right? Which is exactly what we defined on the previous page, but instead I said the probability of x and omega I, right? But they're equivalent to one another, right? I can rewrite, or if I want to represent that in the same form that I represented on the previous page, what I'd have to do is I'd have to swap this conditional probability around. So now this is the probability that given a pixel at position x, it's of that land cover type. So the probability that given a pixel at position x in n-dimensional space, that pixel is class type omega I. And if you just listen to that wording a little bit, that's where we want to get to, right? This is give me some unknown pixel, any pixel in the scene at position x, and compute the probability that it's grass. Compute the probability that it's water. Compute the probability that it's concrete. Right? So this term right here is the term that we want to use to classify a pixel. Because we want to classify a pixel to be the land cover type that it's most probable of being. Right? And that's what this term right here represents. Right? I can't train for that. Right? To train for this, to come up with this probability density function, I would need to pick data in some way that I can isolate that cover type. But the only thing I'm given in this case is all the pixels in the scene, x. And I'm given all the pixels. I have no way to come up with what the probability is. So somehow I have to back into that answer. So if we set those two joint probabilities equal to one another, right? So this is the probability of x and omega I. This is the joint probability of omega I and x. They're equal. Okay? So, but we had them equal to two different things. We had them equal to this, which we were just talking about, and on the previous slide, we had them equal to this. Right? So the different term is this one right here. This is the probability of x given omega I. That's my histogram for that particular cover type. This is the probability that given x, it is in class omega I. I don't know that. What's this? Probability of x? That's just the histogram, the n-dimensional histogram of the scene. Right? So I know all the terms except this one. So let's solve for that one. All right, so let's set these two joint probabilities equal to one another. Then I'll take the product from the previous slide and the product from this slide that represented the joint probability right up here. Rearrange, solve for my unknown term. All right, so I'll just divide by p of x over here. And what do I wind up with? Well, I wind up with the probability of x given omega I. That's a class conditional probability.
But that we had to manually go in and pick stuff for.
With training data, going in, picking some pixels in the scene, I can go in and I can derive that history from data. P of omega I, that was my a priori probability. I could look at the scene and make a guess. Right? It's 50% water, it's 10% this, it's 40% concrete. Or I could just make the simplest assumption. I want to break it up into 10 classes, and I'll make them all the same. Right? All 10% probably. But at least you can make an estimate of that one. That one's easy. The denominator here, that's just the n-dimensional histogram of the scene. Right? So you just do however many bands you have, you do that dimensional histogram. 3 bands, you come up with 3-dimensional histogram. All right, but if you think back to your univariate stats that you saw, you've seen this before, or at least you've heard the name, and this is called Bayes' theorem. Okay, is everybody good to that point? A lot of times it just takes looking at the definitions and reading them through and trying to restate them a little bit, but I want you to really understand where that's coming from.
So that one, I'll have to have training data.
This one you have to have training data. This one, you make some educated guess.
You have to know the number of classes.
You have to know the number of classes, and you have to be able to look at that scene and come up with rough percentages. This one is just a histogram of all the pixels in the scene,
Is there a
regardless of
mathematical,
class.
is there a mathematical way to tell if you've done a good job? Like not just visual inspection of like, oh, yeah, I did a good job picking out 5 classes, but mathematically running a bunch of them and seeing what comes best?
Yes, I think. Let me see if this will answer your question. You could pick n classes. You could then classify every pixel in your scene, and you could see how well you did by picking another set of training data and seeing, how well you classified that set of data. So I don't know that that's really, you want to know how many classes there are.
Well, not just how many classes, but also the probability of the class I.
This one, the paper error probability.
Yeah, because it seems like that's going to obviously make a big difference on how you're picking your data.
Well, I mean, it definitely has a big effect on your answer. And what do you mean by it
So if
has an
you,
effect on how to pick?
say we had, to make it simple, like 3 classes, and so we could come up with a billion percentages, but just to be simple, we'll do like 33% each, and then maybe we'll make one 50%, and so on, and we come up with a certain amount of probabilities.
Yeah.
And then when we run them all, is there a way to say, without just visual inspection, this is the best classifier in some kind of like mathematical sense? Or do you have to do this stuff visually? Did I make my question make sense?
No. I know exactly what you're saying, and I wrestle with that all the time. Can I table that for one? Well, let me give you the brief answer, and you're going to do this in the lab.
Okay.
All right, so if you had a way of taking a scene and throwing it to some algorithm, and the algorithm came back and it classified all the pixels, and it gave you back a map of all the pixels put into classes, and you didn't have to do anything, that would give you that answer, right? So if I could say, hey, here's a scene, go pick as many classes as there are statistically unique in that scene, and give me back a map. And it might come back and say, you know what, I found 47 very unique classes in this scene, and here's a map of them. And then you can go count pixels in each of those classes, and that would give you those probabilities. That would give it to you perfect. The problem is you don't know what any of those classes are, right? Because you let an algorithm pick them, and you didn't have any input to that. That's the mathematical way to do it, is to statistically isolate classes.
But it seems like a lot of this is based off of just visual inspection then.
Well,
There's no like, I don't know what the word is for it. There's no like metric to say this is good or something like that.
Well, no, I think that is probably your best metric. If you can say, go in and within some probability, right? You have to assign some threshold values. Go in and give me as many classes as you can find in that scene that are statistically separable from one another. Right? Then you can definitely have this value. Get this value back. But when you want to run a classification, you typically want to give names to things in the scene, right? Because I want to find all the roadways. Well, you can let an algorithm go classify all the pixels, and then afterwards you can say, you know what, class 14, 17, 23, and 84 are roadways. So let me combine those all into one class. They might not be statistically the same at that point, though, right? You could have concrete roadways and asphalt roadways. And if you went in and trained, and you went into a scene and you started picking roadways throughout the scene, how cognizant would you be to say, you know what, am I picking concrete or asphalt roadways?
So it'd almost be
You know-
better if after you pick the training data, it's still separated within your training data and then combine them together at the end.
Absolutely. Absolutely. The best way to go about classification is to try and think non-culturally, but think statistically. And can these things be separated? And if I pick roadway 1 and roadway 2, and they're different materials, well, I have to get past the urge to say, I want to pick roads, because roads aren't necessarily going to be separable. But if you could pick road type 1 and road type 2, and then after the fact, combine those two together, after you do the classification, combine those, you get a much better classification. Very few people do that, because it's very hard to do. Right? The softwares that are out there to do classification aren't set up to do that. You have to go through several steps in Envy to get there. But it's, all the tools are there to achieve it. All right, so Bayes' theorem. This is what we want to solve for. This is going to be our answer. That's going to tell me which pixel given a pixel at x, or I'm sorry, which class given a pixel at x is most probable. So you can imagine in the end, if I have 5 classes that I'm trying to classify, I'm going to have 5 probabilities that look like this. So for every pixel in the scene, I'll have a probability that it's grass, that it's water, that it's forest, that it's concrete, that it's asphalt. 5 probabilities. Which one is it? It's the most probable one. So that's the term we want to come up with. All right, now, how do we get these terms? Or how can we represent those terms? I said we can come up with this term. This is essentially the histogram. But we could represent it as a particular type of distribution of the lines. So if I went in and trained, if I went into my scene and I picked out a series of pixels and said that they were asphalt, I can compute for that set of pixels the mean and the variance, right, if I was just using one band. And I can come up and represent that probability density function as a Gaussian. Right? This is a Gaussian distribution. You have your z-score up here, you have your scaling factors out here. This will give you your Gaussian distribution. All right. Now I can do that, right? I can take all that data, I can compute the mean, I can compute the variance term, just like we have down here, plug those in, and I get a probability distribution function. I could just use the histogram, right? The histogram also gives me this. If I go to, let me just jump ahead here 1 sec. If I go to the multivariate case, this is the probability density function, and this is the multivariate Gaussian, as opposed to the univariate Gaussian, which was on the previous page. It's the same, right? You got e to the -1/2 times x minus mu squared, right? Transpose times that, but this is a vector product, divided by the variance. But in this case, it's pre and post multiply the covariance matrix, or the inverse of the covariance matrix. Okay, so remember, this mu sub I is the mean of a particular class type. Capital sigma sub I is the covariance matrix for that class type. And this term, if you look at it, try and remember that. I go back 2 slides here. It's the same as that term, essentially, just in multivariate space. And so is the scaling factor out front. We have the n over 2 root of 2 pi, as opposed to the square root. Right? Because in the square root case, this would be 1 over 2, which meant we had 1 then. Here we have the n over 2 root. And here, this is the determinant of the covariance matrix. The square root of the determinant of the covariance matrix. Okay? what did we have in the previous case? We had the standard deviation. This is essentially the square root of the variance, which is the standard deviation, right? But in this case, it's the covariance matrix. Now, the reason the determinant is taken there is the determinant of the covariance matrix is very representative of its size, right? What does that even mean? If you have a big determinant value, right, the determinant of that covariance matrix turns out to be a large value, in general, that means a lot of the terms in that covariance matrix are big. It means your class, when you plot it in n-dimensional space, is very spread out. And the variance, or the covariance, is very large in that n-dimensional space. It's the same thing, it's the same equivalent as a large standard deviation, meaning your Gaussian distribution is wide. Right? A large determinant of a covariance matrix means your covariance matrix represents a class that's spread out in all directions in n-dimensional space.
But when you take the determinant, actually, you take the cross product and minus the cross product, so you have a difference. So even though it's a big number, you have difference.
But the terms, I know what you're saying, and in a two-dimensional case, I agree with you, but you're talking an n-dimensional case
Even
here.
if it's n-dimensional case, still, you just go and do it, right, recursively for each one.
But if you look at the covariance matrices, the terms that are along the major diagonal are variances. Those tend to be very large. If the data tends to be highly correlated, or if the data tends to be uncorrelated, what do the off-diagonal terms tend to be?
Large. The off?
The off-diagonal terms.
If they are uncorrelated, 0.
Right. So if you have data that is not all very correlated to one another, you'll tend to have those small off-diagonal terms, which tends to push the magnitude of this whole determinant high.
So what does it mean to have correlated data in that sense?
So correlated data in this sense, remember, is that well, let's talk about the correlation matrix for a second, right? Remember the covariance matrix can be derived from. The correlation matrix represents how correlated is band 1 to band 2, band 2 to band 3, and any two band combinations, how correlated are they with one another? It represents redundancy in the data. If two bands are highly correlated, they represent the same information, essentially. Right? If they're uncorrelated, they have very unique information about what you're looking at. So if you were to plot band 1 versus band 2, and the data all arranged itself in a nice 45-degree line, the data would be highly correlated, and either one of those bands could probably be used in place of the other. So that's the correlation in this sense is band-to-band correlation within a class. And because band 1 and band 2 might be very highly correlated for graphs, but that might be very weakly correlated for concrete.
Okay, so in the n-dimensional case, we're just going to assume that those cross-correlation terms are not that significant.
No. We're going to assume over the length of the entire reflectance spectra that we're going to have some unique information, and that some of those terms will be. Ones that are close to one another are always going to be very highly correlated. Because if I draw any spectra.
Right, but in order to get that determinant to be significant of the variation, or kind of representing the variation in the scene,
Okay.
are you assuming that?
Yeah, no. All right, so I know exactly where to go.
Okay.
All right, so that the band-to-band correlation says that if I know this band, I can predict this band. If I know this band, I can predict this band. That's the correlation. Now, if I'm training and I'm picking grass pixels, so let's say this is a grass spectrum, and I go out and I choose a whole bunch of pixels, and I get a whole bunch of spectra that fall right on top of each other. right? That means I did a really good job at picking the same type grass. Right? And if I plot that in n-dimensional space, I'm going to get a pretty tight cluster in n space. Now, if I'm sloppy and I go out and I pick very healthy grass, and then I pick dry grass, and I pick different species of grass, now all of a sudden I'm going to start to get spectra that form this huge envelope. Right. So now in any band, I have a very widespread representative set of data. So in that band, my variance is going to be very high. Okay. So when I start to come up with very high variances in each of the individual bands, then my major diagonal terms of my covariance matrix are all going to get very big. My off-diagonal terms, which are based more on the shape, because it's very correlated with one another, right? They're going to tend not to take a lot of power away when you compute the determinant. So what you always want to shoot for is curves that lie right on top of each other. What you typically wind up with is something more like this. It's hard to pick up spectral signature. All right, we talked about this the other day when we were talking about Mahalanova systems. Right? We can have 3 different distributions, different means, different standard deviations, and okay, which pixel does, if I have a pixel at this digital count right here, 125, which class does it belong to? Right? Well, it belongs to all 3 of those classes. Right? It falls under the distribution of all 3 of those classes. Well, which one is most probable? It's this one right here, the red one. Okay? So what this P of omega I given x conditional probability is going to give us, is it's going to give us the probabilities for this class, and this class, and then we can choose which one to assign it to. All right, so let's look at an example. This is a Landsat thematic mapper scene. This is Rochester airport. RT is like right here. Should have picked that better. Rondequoit Bay, Genesee River. All right, so what did I do? I went in here and I picked 5 classes. I picked some Rondequoit Bay water. Rondequoit Bay at about around this point right here is about 100 feet deep, very clear, very dark water, not a lot of suspended solids in it. The Genesee River, you could even see right here how bright it is, right? See, I mean, that doesn't look as dark as that water right there does, because it is different. There's a lot of suspended solids, a lot of chlorophyll floating in the river. So I picked river water as another class. Let's see. I went over to the golf course, Genesee Valley Park, and picked some nice golf course grass. Picked Marketplace Mall, right? That's a horrible thing to pick. Think about that. Marketplace Mall. What's Marketplace Mall? Stone roof, HVAC units, asphalt parking lots, cars parked everywhere. Right? That should be, keep that one in mind, that should be a very bad class. Okay? Bear Field, over at the, what's there now? MCC is, no, this is the 390 split, so this is 590 coming off this way. It's still just a bunch of empty fields there. This is Winton Road, right over here.
So this is going to be based off of digital counts in your red, green, and blue?
No. In this case, we're going to base it off of red, green, blue, and the infrared bands also. Not the thermal band. But in Landsat, we're going to do 6 bands. But what I'm showing you here is bands 3, 2, and 1.
But I mean, just because the digital count might be similar in like a RGB image doesn't mean that they're going to be
Absolutely.
like the river and the roads?
Absolutely.
Okay.
Yeah, I mean, if it looks similar in RGB, it might be extremely separable in bands 4, 5, and 7. Absolutely. So, what you can do while you're doing all this, if you're in a package like Envy, you can click on a pixel and you can plot its spectra. So you can start to, I mean, you start to look at spectra as you're picking training samples, and that helps you. You pick things that are spectrally dissimilar. All right. So from these 5 classes that I have here, which one do you think are good? That one's probably really good. Right? Nice dark water. Nothing much else going on there.
Like golf course grass.
Golf course grass is probably pretty good. Nice and uniform. If it's not, people don't like playing at that golf course, so don't come back. That's not a good one, right? That's probably not a good one either. That's you know, dug up dirt with scrub grass growing all over the place and bushes and you know, probably all kind of stuff that's put in there. The river water is probably pretty good. I mean, the Genesee River is well mixed and it has all that stuff in suspension and it's pretty uniform. So that one's probably pretty good. All right, so how do you start to look at this stuff? And you know what? We might go offline for a second here. But let's take a look at this and we'll do this in real time. All right, so what do I have? If I plot band 2 versus band 5, and I just arbitrarily picked those 2 bands. Here's the bay water, nice tight cluster. Here's the river water. Except for that point, it's a pretty nice cluster. There's golf course grass, bare field, and then here is Marketplace Mall. All right, that's not a good one. There's a tight cluster here, but this stuff's really going to skew that covariance matrix. And it's really going to have a big effect on it. All right. So let's bring up Envy. I hope I have this stuff here. That was our other class. All right. So let's open an image. I think that's the image. Yeah, all right. So there's that image, same one that was in the notes. All right, so we've got a little bit bigger. All right. So if you haven't used MV before, you always get this 3-window view, except probably in about 4 months, this is all going to look totally different because MV5 is going to come out and they went to a 1 pane view. So you're getting trained on the last version of MV that's ever going to look like this. The next one's very neat. All right, this one down here is what they call a scroll window, and this red box is what you're seeing up here. So this is the image window. You can move this red box around and get the different parts of the scene. Okay? And then this little red box is representative of what you see in the scroll window down here. Okay, and there's a plus and a minus button here where you can scroll in farther or further out. Okay, so that's how you navigate around. Now, what I'm going to do is I pre-picked some regions of interest, and what we'll do is we'll lay those on here. Under the Tools menu, there's a region of interest submenu, and this region of interest tool is what you're going to wind up using in the lab to go and pick your training samples. It lets you select your region, lets you name the region, lets you give the pixels that get lit up around it a color so you can tell them apart from one another. It's a pretty robust tool. Well, let me just pull up some ones that I have here. Yep, that's the ones that were in the exam. All right. So I restored them, and if you then, once you restore your regions of interest, if you open up the ROI tool, you could see that red is golf course grass, blue is bare field, yellow is bay water, and now you can see that they're actually out here on the image itself. All right. Being able to visualize your information is amazingly helpful when you're picking these kind of regions. Because what do you want these clusters to look like? How do you want them to relate to one another? if the idea is to separate them, to be able to classify things into different class types, how do you want these clusters to appear when you plot them like this?
Spread out and concentrated.
Spread out and nice, tight, concentrated, if that's at all possible. Okay? So, if I could somehow come in here and lasso those pixels, and these pixels, and these ones, and not get any of the other ones in there, that means I did a really good job. But typically you're going to have lots of overlap between classes, especially as you start picking more and more classes. These 5, I spent a lot of time trying to find ones that separated like this. And I wanted to get one really bad one here, as an example. But being able to visualize is key. So you can go in, you can make plots like this, one band versus the other, and look at it. And then you got to plot, like Maria, like you said, just because they're not separable in red and green doesn't mean they're not separable if you include, you know, the IR. Right? So you can imagine doing this in 2 dimensions. You can imagine doing it in 3 dimensions, right? You can plot 3-dimensional clusters in 3D space. How about imagine doing it in 17 dimensions? That's one of those things you always wish for, right? Can I visualize data that's more than 3 dimensions? And you say, oh, well, you can imagine what it looks like in 4 dimensions. All right, well, one of the prime authors of ENVI, his name was Joe Boardman, and for his PhD thesis, he came up with tools to help with classification. And one of them was a tool called the ENVI Visualizer. And this is, I think, one of the coolest tools that's out there now. All right. So if I go under my ROI tool, under Options, and I pull down, there is a tool here somewhere. Okay, where you go? Oh, it's under File. I'm sorry. All right, so under, of course, you have a tool that's under File. Right here, there is Export ROIs to ND Visualizer, N-dimensional visualizer. All right, so if you choose that, it's going to ask you the image you want to work on. And if you have more than one image loaded in ND, you'll see all those images here. Right? But we only have one loaded, so I'll select that. You can then pick the bands you want to use. Remember the other day we said there's going to be some bands in this data that aren't good? You would use this tool right here, a spectral subset, and allow you to pick which bands you want to use. And I'm going to use all of them in this case. All right, so I'll hit OK. Then it'll ask me which regions of interest that are currently open, which ones do I want to use, and I want to use all of them. So I'll select all of them. And hit OK. And then I get up this tool. All right, so here's my ND Visualizer. As you can see, doesn't it give you an amazing amount of information? Get this nice black screen. All right, then you get this display over here, 1, 2, 3, 4, 5, 6. All right, what these are the bands. All right, you could pick any bands you want and plot. So if I want to plot band 1 versus band 2, there they are. All right, if I want to plot band 2 versus band 3, there they are. If I want to do band 2 and 5, that's the one I had in notes, there they are. Now you can see that in the 2 and 5 plot, I got some nice separability, but in the 1 and 2 one, look at all that overlap. Right? That's because these bands are very correlated. You can see they form a nice line. All right, now what I can do, this is an ND visualizer, I could view it in 3 dimensions. Right? You could obviously see the difference. Right? Nothing's happening there, right? All right, because you're still looking down the 1, 2 axis. You're looking at 1, 2 in the plane. 5 is coming out of it. All right, so what do they let you do? They let you start it rolling around. So he randomly just rotates these 3 axes. And what that does is it gives you an opportunity to say, is there any place that I could rotate this 3-dimensional space to where everything is separated? You could slow it down. A little speed button here. Right? But what you want to look at is say, hey, did I do a good job? Do I have separation? Right? And you can turn on your axes under Options, say Show Axes, and you can see the 3 axes. That's kind of weird. That's the first time I've ever seen that happen. All right, you can see your 3 axes. All right, now, what if I wanted to visualize this in 4-dimensional space? You turn on band 4. There's 4-dimensional space. Those axes are going to flex relative to one another. So those axes are no longer fixed. They're flexing in space, and the plot's happening where these non-orthogonal axes now are there. But because of that flexing and this kind of mushing around of this 4-dimensional space, you can now see if you get separation. And you could do all 6 dimensions. So there's all 6 axes. And now if you look, at some point you're going to see very complete separation of all that data. This is a great tool, you know, to be able to look at this kind of data and try and figure out if you're doing a good job.
Very cool.
That's neat. And Joe Boardman's, if you ever have a chance to meet him, he's a great guy. Really smart. All right. You could, you're all staring. I do the same thing. it's hard to look away from. But it does, it gives you an amazing amount of information. So as you're training your classifier, every so often export your ROIs to this and say, hey, am I doing a good job? And look at those pink points. They're everywhere, right? They're overlapping everything. And if I am going to form an n-dimensional Gaussian distribution that's going to incorporate all those points, how big is that n-dimensional Gaussian going to be? It's going to spread all over the place. It's going to incorporate everything in that space. So I'm going to get way too much false alarms because of these points out here. This is a pretty good cluster. So probably when I pick the roof of Marketplace, which is probably the majority of that, that's just probably stone thrown on roofing rubber. That was probably a good cluster. But when I included all the parking lots and the cars and stuff like that, it became not a good class anymore. So you go back and you refine that region of interest. And throw it out, pick another one that is represented. And you want to make sure you do that in order to get the best chance of separability you can get.
If you choose more than one image, what it means? Like, so it's more channels, or?
I'm sorry, what?
If you choose more than one image.
These are bands.
Yeah, I know. I'm saying that when you open this option, you add an option to
You can only choose one.
one image.
Yeah, only one at a time.
How do you do urban classification then, when you do want to have an extremely variable scene and have cars and roads and all that stuff?
These techniques work. You just have to be very, so if you want cars as a class, then you have to do red cars, green cars, blue cars, all separate.
I mean all together though,
You have to do them separate and then combine them after the fact. Absolutely.
because it makes just a little bit with all the rest of your more pure classes.
Exactly. Green car and green grass in just RGB look the same. When you include the chlorophyll bands, now you can separate them. Right? But green car and red car look very different in visible. But as you get out into the infrared, they'll tend to look the same, right? Because you're just seeing the binder, when we're seeing the dyes, not those wavelength regions. So you have to be unfortunately, you have to be very careful when you're trying to do an urban scene. It's a very tough situation. All right, now, that's all make sense? All right, so let's hop back here for 1 sec, and let's just take a look at the covariance matrices for a second. So for the urban and the Baywater, remember the urban was that real spread out pink cluster, and the Baywater was up in Aronnacoit Bay, that was that yellow one on the real deep water. You can print these descriptive statistics out of Envy. These are just screen grabs from there. And for bands 1 through 6, it's actually bands 1, 2, 3, 4, 5, and 7 of Landsat, but they're just labeled 1 through 6. You get the min and the max for each band, you get the mean, you get the standard deviation. So you can see that for that urban scene, the standard deviations are pretty high. For the Baywater, they're pretty low. That's what you expect when you're looking at those clusters. The covariance matrix for the urban, look at some of these terms. Look at the determinant over here. Right? It's times 10 to the 11th. This one, all the terms are very small. It's on the order 10 to 2. Right? So there's 9 orders of magnitude difference in the determinants. And if we go back and we look, you know, this class right here, you'll spread out compared to this one. So you'll always see that correlation between the determinant of the covariance matrix and the spread of that class in n space. So, any questions?
After you were saying that you did it separately for each one of the classes, right?
Yep.
And then you were saying that you combined them. What do you mean that we combined?
Okay, so in this particular case, I wouldn't do that because I only picked 5 classes and they were all very distinct. But let's say I wanted to go into more detail, and I had an image, very high resolution of downtown Rochester, and I wanted to classify cars as one of my classes. Because cars look so different colors, there's no way I could pick all the cars in the scene as training samples and come up with one class. I'd have something that looked like this.
So as you said, each car will be separate class.
Or
Okay.
all the white cars, all the green cars, all the blue cars.
Okay,
And then classify the scene. And then once I get a class map out, once all the pixels have been assigned to a class that I've picked, then take all the red cars, the green cars, the blue cars, make them one class called cars. Right? So just post-combine them together. If that's what you wanted to do. I mean, you might have a situation where you want to look for white cars.
so but you just get like another class with big variance.
No, because your product at the end is a map. It's a map of what every pixel is.
Right?
And then all you're doing is you're combining 3 colors in the map together to form one color, imagine, and that one color would be all the cars. No longer are you doing the statistics based on this. You already used the statistics to classify all the pixels.
Okay.
You have your answers. Now you're just in
So
post-processing.
okay, so just give them like one label.
Yep.
So that's what you mean.
Exactly. All right, so why don't we take 5 minutes, and we'll come back and we'll do, let's do a classification of this and see how it works. So let's take a look at what's behind Gaussian maximum likelihood classification, or people will often refer to it as GML classification. All right, so we'll go through sort of a derivation of the underlying equation. Then we'll take a look at it, and then we'll go through and do an example. All right, so let all the classes in a scene be represented by omega sub I. Right? So in this particular case, we're going to have m classes. All right, now we want to determine all the conditional probabilities that say the pixel belongs to class I given its location x for all m classes. And our decision rule for classification is going to be the same. Well, we'll write it here, but we'll change it to the same notation in a second that we used on Tuesday. That x is going to belong to class I if the probability of belonging to that class given a pixel x is greater than all other probabilities for x belonging to all the other classes. Right? So in other words, probability is the highest, we'll assign it to that class. Okay? So x will be an element of the class if the probability is higher than belongs to class I than for all other classes. Okay, so we have Bayes' theorem. That's going to give us the conditional probability that we need. So let's rewrite that rule that we just had on the previous page for a sec. Here's the probability of omega I given x. Here's the probability of omega j given x. If you look at that inequality, you notice the denominators are the same. Right? So they can go away because they won't change the direction of the inequality. And what are we left with? Well, we're left with this term here where I have the class conditional probability that I know I have a pixel at position x given I'm looking at class I times the a priori probability for class I. As long as that's greater than that same class conditional probability for class J and multiply by its prior probability, then I'll assign it to class I. All right, so what did I do? Well, I got rid of this term, right? It's gone now. I can measure this. That's I measure from my training stats. This I make a good estimate. This is from training stats and another good estimate. So our unknown here goes away just through Bayes' theorem. All right. So our decision rule comes down to be this. Okay? As long as that inequality is true for all I not equal to j, we can assign it to class I. All right. So we can go into the shorthand that we had before, where we had g of I of x and g of j of x. They'll just be equal to those probability products from the previous slide. And those are the discriminant functions which we referred to the other day. All right, now, in this particular case, what we're going to do is we're going to form this discriminant function as follows. We're going to take the natural log of each of those terms, g of I of x and g of j of x, okay, and substitute them in. And why we take natural log will become obvious in a second. It should become obvious right now. We're going to assume it's Gaussian. There's an e in there. And that gets rid of the e. Okay? So if I have the natural log of a product, that's the sum of the two natural logs of the individual components. And now let's go and plug in some stuff. All right? Let's see what we have here. We have the natural log of the prior probability and the natural log of essentially the histogram, probability density function. If we make a Gaussian assumption for the probability density function, then what do we have? We have the natural log of p of omega I, the prior probability. That didn't change. And then the natural log of the multivariate Gaussian normal distribution. Okay. We got omega sub I and sigma sub I from training data. And then we can go ahead and we can compute that Gaussian, that multivariate Gaussian. All right, now since we've taken the natural log of this, the e goes away eventually here. What did I do? Oh, I just brought everything up into the numerator. And now I could break this product apart into the natural log of the prior probability, which we had before. And this product breaks apart into the natural log of 2 pi to the n over, minus n over 2, so the n root of 2 pi. Then we add to that the natural log of the square root of the determinant of the covariance matrix. All right. Then we have the natural log of e to the minus 1/2 times that term right there. What was that term? What did we call that the other day? Mahalo distance. All right. So now, here's why we did the natural log. The natural log gets rid of that e. All right. So I wind up with this term. I have natural log of the prior probability, natural log of 2 pi. I can bring the n over 2 and the minus sign out front from the exponent. I can do the same with the minus 1/2 here, and I have the natural log of the covariance determinant of the covariance matrix, and then I subtract from that the Mahalo distance. All right, now this term is class dependent. Right, the first term here, the natural log of the prior probability, is class dependent. That'll be different for each class. This term is a constant. Right, for n bands, this will just be a constant. So we're going to drop that term out, because that's not going to affect anything. This is class dependent, because it has the class covariance matrix in there. And obviously this is class dependent, because it has the class covariance matrix and the class mean vector. So we'll call our discriminant function in this case all the terms here that are class dependent, which we can drop out that constant. Because that won't change the direction of the inequality, so we can just get rid of that. All right, so here's where we wind up with. This is our Gaussian maximum likelihood discriminant function. And I think it really, if you look at it carefully, it's really quite neat. All right? I want g of I to be big. Right? The bigger it is, the more likely the pixel that I'm looking at belongs to the class that I'm concerned with. Right? So I want this to be big. All right, so let's take a look at these terms, and let's actually go from left to right. So let's just use the first term. So let's say we truncated this whole thing to just give this first term. What is that? That's the natural log of the prior probability. That was what's the likelihood that, just given all the pixels in the scene, what's the likelihood that it's grass? What's the likelihood that it's concrete? And that's what we said we can get from a visual inspection of the scene. If that was my only determining factor, I mentioned this the other day, right? If I said if a scene was 80% water, 10% grass, and 10% concrete, and I asked you, hey, here's an unknown pixel, I'm not going to give you any stats, I'm not going to give you anything, what class does an unknown pixel belong to? You probably go with the 80%. Right? So if our classifier was only that, only what's highlighted in blue there, that would be our classification. 20% of the time we'd be wrong, 80% of the time we'd be right. Right? But that could be our classifier. All right, now let's do this. Let's go one term further here. If I'm going to subtract off from this, remember, larger the better, right? If I'm going to subtract away from this term 1/2 the natural log of the determinant of the covariance matrix, what does that mean? What did this term represent?
Square root of the determinant.
Essentially, it's the square root of the spread of the data, right? Some measure of variance, in this case, the covariance matrix. The urban scene, which was the urban class that was all spread out, had that covariant, the determinant that was like 10 to the 11th, right? So if my data is really, really spread out, meaning that it's going to cover the entire n-dimensional space, and essentially it's going to really confuse everything, it means it's a poorly chosen class. So what am I going to do? I'm going to subtract that value away from this initial guess at what the pixel belonged to, which class it belonged to. So I'm going to penalize that decision.
Same thing happens when you are choosing like a big region of the class, because as big as the region of the class that you're saying it's a region of interest, like class 1 or class 2. So if you take a big region, so you have more variances, like you have more probability to get like more. So it's like always the trade-off between like getting like more reliability,
right,
class that represent statistic that represent this class, to the one that like it's too big and it's like not the real data.
Absolutely, absolutely. So agree wholeheartedly, and that's why you want to try not to do that, right? So you don't penalize. All right, now, so if I have my data really spread out, I'm going to penalize my decision for that particular class. Now let's look at the last term. What's this? This was the Mahalanobis distance, and that was the statistical distance that you were away from the mean. Right? I'm subtracting that away. So what does that mean? If the Mahalanobis distance is large,
You're probably not belonging to that class.
you're probably not part of that class. So let's penalize that initial guess. So we make this initial guess. That's our guess at what class it belongs to. We penalize it if it's far away. We subtract off that Mahalanobis distance. And we penalize it even further if we have a very variable class. So that's what Gaussian maximum likelihood is all about. Right? That's the physical interpretation of what's going on. And it's kind of sad because a lot of times most people ignore prior probabilities. They just say, oh, just set them all equal. Right? But that's really your most important factor. Everything else is a penalty against it. Now, remember, we could have got rid of all this. Right? We could have gotten rid of everything in blue there and just made our discriminant function be the Mahalanobis distance.
If it's the same for all the classes.
Then it's, what's that?
If it was the same for all the classes.
If what was the same?
The prior probability.
If it was the same for all the classes, then essentially it's not even there. Yeah, exactly. And if all the class covariance matrices had about the same determinant, that would go away. But that's the assumption that you're making, is that you're really not going to care about the spread of that data if you just go ahead and use Mahalanobis distance as your discriminant function. Right? And that's a choice. You can do that. A lot of folks do that. But you have to be very aware that you're now ignoring prior probabilities and you're now ignoring spreading your data as a possible penalizing function.
We have a little trouble with what you're subtracting in terms of one half the log and the other one.
Yeah. Well, see, in this case, it's just a number. now, right? So the only reason I took the natural log was to get rid of that e.
Right.
Right? There was no physical meaning to taking the natural log of the a priori probability, but it's just a number, and it stays ordered, right? So if the prior probability is large, the natural log of that will be large. If the prior probability is small, it'll be small. So the order stays the same. So that's what's important in this particular case. This 1/2, just comes out because you had the minus 1/2 up here, so it just came outside of the natural log. But the important part here is how spread out is the data. Okay? And if this is big or it's small, this whole term will tend to be big or small in the same proportion. So the discriminant function is going to move down proportionately, depending on how much you're subtracting off. Right? And then this one's just a pure distance. So don't think about physical units here, right? I mean, because this is actually a distance in digital counts, right? But what is that? That's a unitless quantity, right? Because digital counts don't have a quantity. They're just an arbitrary number assigned based on brightness. This is a measure of variance in brightness. Okay, so at least these two terms have the same non-unit, right? This one's strictly a probability term. Okay, but they're all unitless quantities.
And they are comparable. I mean, usually.
I don't know. I mean, I'd feel much better if there was units on all this stuff.
No, but I'm saying the magnitude of one term is not usually overwhelmed by the others.
Oh, okay.
Because
Yeah, no, they can be. This, in the case of that urban class, is going to drastically overwhelm all the others. And that's what you want to happen because that class is so spread out. But yes, relative magnitudes between all of them tend to work out with a pretty decent answer. All right. So let's take a look at how this works in there. All right, so I have some regions of interest here. We took a look in the MD visualizer, and they look pretty good. So let me just close that. All right, so let's go ahead and do the classification. So there's a classification menu. You'll do this in the lab. Supervised classification. There's a whole bunch of different classifiers that you could choose from. We looked at minimum distance and mean. We looked at Mahalanobis distance. We looked at maximum likelihood. We'll look at spectral angle mapper in a second. We'll look at parallel pipette in a second also. So we looked at majority of them in here. There's some neural network and SVM, support vector machines, classifiers in here also. You'll look at both of those next quarter. You'll look at this one next quarter, support vector machines. Neural nets, if you take the pattern recognition class, you'll see that in there. All right, so let's go ahead and choose.
Random Markov fields,
What was that?
the random Markov fields,
You see that one in pattern recognition also.
Yeah, in pattern recognition.
Pattern recognition. All right, so maximum likelihood, Gaussian maximum likelihood. Choose the image. You can choose a spectral subset if you don't want to use all the bands. You'll wind up doing that in your case. Spatial subset is you don't have to do the whole scene. You can just do a part of the scene if you want to. And all right, so you can see over here, you always get some information about your image that you selected. Make sure you have the right one. So we're going to pick that image. We're going to pick all the bands. Select the classes from the regions that I want to classify into. So if I want to classify all of them, I pick them all. All right, now set probability thresholds. These are your prior probabilities. No. Yes, yeah, these are your prior probabilities. All right, notice what the default is. It is make them all the same. Right? If you wanted to choose multiples, you can put in one for each. Right? So you could actually input a prior probability for each one of the classes. In this case, let's just leave them all in, right? Since that was the default. I just want to run through the mechanics here to make sure you see what's going on. All right, this probability threshold, I'll show you that in a second. But you can imagine, well, let's look at it before we do it. If you look at this term, this Mahalanobis distance term that we have here, it's a quadratic term. The boundaries in n space will tend to be parabolic, elliptical in nature. Right? So if I were to go and, let me up here, if I were to take my original data and plot those decision boundaries, remember the other day we drew straight lines between classes and said, hey, if I have one band, if it's to this side, it was grass, if it was this side, it was asphalt. And then we took the two-dimensional case and we drew 3 lines and it separated 3 classes from one another. But that was minimum distance to mean. Those boundaries tend to be linear. In this case, the boundaries tend to be elliptical. So if I take my data and I compute the mean and covariance matrix and I compute the Gaussian statistics, or the Gaussian distributions, and I plot that in 2 space, again this is band 5 versus band 2, so same visualization as we saw before. In this map right here, you can see that anything that's in this blue area is going to get assigned to that blue class, which I don't remember what that one was. But the yellow one down here, remember, was the lake, the bay water. This was the river water. This was the golf course grass. This was the urban, right? So it says, hey, if I fall in this little spot in 2-dimensional space, I'm going to assign it to bay water. Actually, what we're going to do is we're going to look if we fall in that hyperellipsoid in 6-dimensional space. I'm going to go to that class. And same thing here, same thing here, same thing here. But if I happen to fall outside of any of those, I'm going to be marketplace small. Right? So it's big class. But because this is quadratic in nature, we could pick a chi-square statistic to do some thresholding and say, you know what? I'm going to make the assignments here, but let's take a look at that blue class for a second. It went from this ellipse to this ellipse. What happened there? Well, what I said was I want to be 99.9% sure that I belong to that class. Right? So that means cut off some of the tails of the Gaussian distribution. So to get to that point and cut off those tails, it shrunk the ellipsoid down to this big. And the red one shrunk, the yellow one shrunk, the cyan one shrunk, and most significantly, this one shrunk. But look at the orientation of it compared to the original data. It's sort of skewed in that band combination, right? Because of this extra data over here. But at least now we're not going to assign a pixel that falls over here to that urban class, or a pixel that falls over here to that urban class. So what will we do in that situation? We're going to leave those pixels that fall anywhere except in these 5 ellipsoids, we're going to leave them unclassified. We're going to say, hey, I don't know what those are. Okay? That's probably the best situation to get into. So if we go back to envy, this probability threshold is the threshold that you want to set to match that. So if I put 99% in there, actually I think it's 0.99. I would definitely read the help on this and see if it's 0.01. I forget which way they specify that. All right. Then you can put your result to memory or out to a file. You can output a rules image. What this is this actually plots the discriminant function as an image. So you get 5 images, or yes, 5 images, one for each class, and you see the magnitude of the discriminant function for each of those classes. So if you wanted to look at that. So let's put it up. All right, so since I don't know what this is, let's leave that blank. So everything's going to get assigned to a class. So we should get a really bad classification in this case. Okay, so we'll let it go. Does its thing, and it's done. All right, so now I have 2 new images that came out over here. One's in memory 1 and one's in memory 2. The memory 2 is the maximum likelihood map. So let's go ahead and take a look at that and make a new display. And load that. All right, so there's my classification. It's terrible, right?
What happened to the Baywatch?
Yeah, the Baywater came out pretty good.
But you're using like the same training image as a test image.
Yes, and you have to do that.
No, you don't.
No, you absolutely have to.
Why?
Because the radiometry is going to change on the scene.
But all the idea is like it's a training data in order to get like the statistic from, and then you have a test image that you want to test or you classify.
That may be the case if you have a scene or a set of data that's not going to change over time. But with remote sensing data, you've got to train every single scene. Unless, before you do this, you remove the atmosphere and you convert this to a reflectance image. If you can go through the radiometric calibration of this image to go to ground reflectance, then you can train once and use it on many images. But if you have data that's just digital count that still has the atmosphere in there, because it's so dramatically changed, the atmosphere can change between day 1 and day 2. If you use the same training data, you'll get a horrible result every time.
So what you are saying that the idea is like that you know part of the image, but the other part you don't know. So
you know representative samples in the image, and you want to assign the entire image to different classes.
But if you know these, so if you know these locations, and this is like not something that is, you know when you're saying it's like a training, so why you just don't know all the rest? Like, what is?
Well, all we're doing here is making maps, land cover maps. There are algorithms, and there's many. I'm showing you just a handful of classifiers here. What it sounds like what you want to do is you'd rather take a digital count, or take a pixel, take its spectra, remove the atmosphere, go to a database filled with reflectance spectra, find a match, and assign it.
By the most probability.
Yeah, and that's what I'd love to do too, right? But that's a whole different approach to this.
Oh, I did the same thing, but I did it for RGB, and like I used the training data. I got like all the statistics, I got like all these trainings, and then I'm having like bunch of tests of images, and I tested all this.
Right, but what are the images? What were they gathered of?
Some other images that I didn't do.
Well, no, I understand, but if you're talking about images that you set up in a laboratory and you take over time, then yeah, your conditions aren't going to change. You can do that. Absolutely, you can do that. But if you're shooting out of from a satellite, and you go one day and then a week later you get another image, the atmosphere is going to be totally different, so it won't work all that well. But if you're in a controlled situation, it'll work very well. Absolutely. All right, so the river water tended to come out pretty good. The bay came out pretty good, except where the Irondequoit Creek empties into the river, into the bay. And if you ever drive down Empire Boulevard and look out, this area right here is very muddy. A lot of suspended solids in there. It's very shallow too, so you can see the bottom. So it's not unusual that we get confused. This is downtown Rochester. It did get the urban pretty well, but I think it's probably a little skewed here. And I don't know.
Red was the
grass. The red? I think the red was the grass, right?
And the blue is like this.
Blue was the bare earth, right? So the grass around the airport, if you ever flew in and out of Rochester, the grass at the airport is dead. And it's brown. And it probably does look a lot like bare soil. The golf course itself looked pretty good. And then all the residential neighborhoods where you have nice lawns, they look like golf course grass. And that's probably not unusual, but I only have 5 classes here. There's a lot more than 5 classes. If you drive out of the parking lot here, you're going to encounter more than 5 classes before you leave the parking lot. And so this was just a very small set of classes that we chose. Now, the image that you have is of the RIT campus. So what you should do before you pick how many classes you want is take a look at that image and kind of get a mental inventory of what you're looking for. And that'll give you a good idea. But you're also going to use unsupervised classification to help you out. So we'll talk about that Tuesday. We'll definitely get to that on Tuesday. So, what's this threshold look like? If I pop back a slide here, we can take our decision rule, all right? And we can make this decision if g of I of x is greater than all other g of j of x's for j not equal to I. We made the assignment of x to omega sub I. Okay, that was our rule. But what we could also do is we could apply another constraint and say, I'm going to make that assignment if this is true and g of I of x is greater than some threshold value. So I want to make sure, you know, just because it was the biggest, I don't want to make the assignment unless it meets some threshold. All right, now, since it is elliptical in nature and quadratic in nature, it tends, like I said, it tended to follow a chi-square distribution. It's, you know, I'm not going to go through this derivation here because I just want to be totally honest, I don't fully understand this derivation, all right? And when it comes down to it at the end, this threshold value, the way that it's spelled out in Richard's book, is as follows. You have minus 1/2 times this chi-squared stat out of a chi-squared table, where you have n degrees of freedom and an alpha value of you name it. So this is your, you want to make sure you're right to within 99%, then alpha would be 0.01.
But when we input it to NB is
I have no
alpha
clue.
or 1 minus alpha?
I have no idea. I would look at the help, because I actually don't know how to set that threshold. All right, but the help file will tell you exactly what that probability threshold is. All right, and then the threshold gets penalized by the size of covariance matrix and by the prior probability also. So, but the thing you need to look up in a table, in a stats table somewhere, would be this chi-squared value. Now, when you put the probability threshold in NB, it'll do all that lookup for you. So, pretty sure the value is between 0 and 100%, but I don't know if it's the error of omission or commission. All right, and so in this particular case, for 6 bands, 95%, I want to assign 95% of the pixels that are in the class into the class, and I'm willing to leave 5% of them out. And I put in a 0.095 or 0.95 in the chi-squared table, come out with a value of 12.59, and then my threshold value is class dependent. Right, so T, the threshold, depends on the class that you're working with because you have the covariance matrix and that prior probability. And we looked at that result.
It should be the threshold between two classes, right? So it should be IJ, like TIJ, or...
Oh, no, it's the threshold. You're saying the discriminant value for class I is greater than the discriminant value for all other classes. That's your main decision rule.
Mhm.
But if that's true, I also want to make sure that this discriminant function is big enough. Right? So I'm only going to look at that discriminant function compared to the threshold value for
the
that.
confidence. Okay.
Okay, so questions?
Can you go back that slide? Okay, so would your chi-squared value, the percentage come from how much black is in that?
Okay, so if I look in the chi-square table and I use 0.95, these ellipsoids will be one size. If I go to 0.99, they'll get larger. Because that'll say, for all the grass pixels in the scene, I want 95% of them to get classified correctly. And I'm okay with 5% of them not being classified, even though they belong to grass. If I did 99% of them, it says I'm going to let just 1% of them not be classified. So these regions will grow as that threshold value increases. Is that what you're asking?
Yeah, I just mean like in the picture in the middle,
Yep.
there's nothing that's unclassified. So is
Right.
that the chi at 1?
Oh, there was no threshold. No threshold applied. So
So
this was just the discriminant function itself.
But if the chi is 1, it doesn't mean that every single potential pixel.
If
That's not
the
confusing.
chi is 1, it might be infinite.
Or
Or zero.
cover everything.
Yeah. So if you look in the chi-square table, my guess is if you do go to a probability of 1, it goes to infinity? Yeah, I think it goes to infinity.
Because then you just basically be ignoring that.
Exactly.
Could you try the transforming with
Yeah.
just for fun?
Let's look. I actually don't know what to put in there.
Okay.
You should, even if you put in like 0.99 or 0.95, that should tell you pretty quick based on how much of that mass
Yeah.
is classified, right?
Yeah. That's 0.95. So, see that a little less of this area got classified. This tends to now look much more like downtown Rochester, like you might sketch it out.
Seems like the river's a little thinner too.
Yep, river's a little thinner. So some of those border pixels where they're mixed, where they're half water and half ground, won't be classified.
And we had a lot of river outliers before, like a lot of extra random pixels. Now we only have a few.
Just a couple over right here, right?
So I think that's classifying 90, so
95%
that's 95% of the pixels.
Yep. Yeah, so you can do one more real quick one. Let's put 100 in there.
Seems like if you do 100, you'll just get what you got last time.
That's what I'd expect.
I think you need to click on the next line instead of
Oh.
the.
No, no, I did get an error there and I didn't read it. Probably should have done that.
I wonder if you go further down, if it pretty much gives you just your ROIs and things that are exactly your ROI.
Oh, if you take it down
Maybe
to
like
50,
0.5,
0.5,
yeah.
give it a try. Give it a try. That's remember your ROIs might not be pure either. So don't be surprised if it doesn't give you just those back.
So maybe it'll just give you the mean of each ROI.
We're good? All right, let's stop there. What we'll do next time is we'll do one last classifier, which was actually another paper that Joe Boardman put out after he graduated. Just another classifier that attacks this problem that we've been talking about of graphs in the sun and in the shadow. Right? We'd like those to be one class. And he came up with an approach that does a reasonably good job of making that happen. Something called spectral angle mapper, which is one of the other classifiers in here. This guy. So we'll take a look at that one, and then we'll look at unsupervised classification.